Okay, so today I'm going to do a few example calculation questions regarding uncertainty calculations. And so here we can see from the notes basically a summary of uncertainty calculation guidelines. And so the rules are basically when you add or subtract two quantities, I should say two or more quantities, the rule is that you add the absolute uncertainty within those quantities. Second, when multiplying or dividing two quantities, you add the fractional or percent uncertainties. Either one will work. Typically in class I will do percent uncertainty just because I personally don't like to work with fractional uncertainties. And so in class you'll see me add percent uncertainty when multiplying or dividing two or more quantities. And then some other guidelines you have to follow. Your absolute uncertainty and your measured value must have the same number of decimal places. Those two things must be consistent with each other. And so just for example, if I were to write the quantity, let's say I measure the length of something, I write down L equals 5.1 plus or minus 0.23. Let's say L equals 5.1 plus or minus 0.23 centimeters. This is not okay because I've got two significant figures in the absolute uncertainty, one significant figure in the measured value. Those two things have to be consistent. And the reason for that is if I'm saying that I know the uncertainty to the second decimal point. In other words, if I know enough about my measured value that I can say with certainty to the second decimal point, then I should have incorporated that into my measured value to begin with. And so the point is these two numbers have to be consistent, and if they're not, then you have to round to make them consistent. And so the correct way of writing this would be L equals 5.1 plus or minus. I would round this up to 0.3. When dealing with uncertainties, it's always better to overestimate your uncertainties just to be more conservative with your answer. And so notice now I've got one significant figure here, one significant figure here. This is correct. The last guideline is that your absolute uncertainty should, when possible, be rounded to one sig fig. So one significant figure in the absolute uncertainty. There's no real reason for that other than it's a convention that IB kind of likes to follow since they changed the curriculum a few years ago. So when you go to college and you do work with uncertainties, that might be different. It's not a hard guideline, but within the confines of an IB class, let's say you should always round an absolute uncertainty to one sig fig. And so these are 4 guidelines. If you follow these rules, then you can do any uncertainty problem that you want to. And so now we're going to look at some, and the problems we're going to look at are kind of complicated. Understand, as long as you follow these guidelines consistently, you should be able to do any problems that you want with uncertainties. So we're going to look at some problems from this worksheet here. Let's go ahead and take a look at question. Let's do question number 1. A metal sphere is found to have a radius of 3.2 plus or minus 0.2 centimeters. Calculate the absolute uncertainty in the volume of the sphere. So let's do that now. First, I'm going to write down the given is R equals, let me go back to the problem, 3.2 plus or minus 2. So let me take this out. So R equals 3.2 plus or minus 0.2 centimeters. And I want to find the volume of the sphere, including the absolute uncertainty. Okay, so plus or minus the absolute uncertainty at the end. The equation for the volume of a sphere, which you don't necessarily need to memorize, although it would be good for you to know, is 4/3 pi r cubed. So the volume of a sphere is 4/3 times pi times the radius of the sphere cubed. Now, it's important that you understand that when dealing with uncertainties, constants do not affect uncertainty calculations. And so this 4/3 and this pi, at the end, they're not going to have anything to do with the uncertainty that we're going to calculate. They do have to do with the volume. They do not have anything to do with the uncertainty in the volume. And so, why don't we go ahead and find the let's go ahead and calculate the volume, and then we can come back and calculate the uncertainty. V equals 4/3 pi times 3.2 cubed. Notice the units. R cubed, R is in centimeters, so this is going to give us the volume in cubic centimeters. And that is going to be equal to 137.26 cubic centimeters. Now, the reason I'm not rounding to one, the reason I'm putting 0.26 and not rounding it, or not putting too many decimals, is at the end, after I find the absolute uncertainty, I'm going to go back and round this number to be consistent with whatever the absolute uncertainty turns out to be. For now, I'm just going to write this down just to have something to work with. And so that's the volume in cubic centimeters. Now, let's see, what are we doing here in 4/3 pi r cubed? R cubed, remember, is equal to r times r times r. And so what operation are we doing? We're actually multiplying the radius times itself 3 times. So going back to our guidelines from before, we can see that the rule is that when you multiply or divide two quantities, you add the fractional or percent uncertainties. Okay, so what should we be doing right now? We should be adding the percent uncertainties in what? Well, in the radius, because we're multiplying the radius by itself 3 times. So if you look at what we're given, we're not given the percent uncertainty in the radius, and so we need to find that. R equals 3.2 plus or minus, and so the absolute uncertainty is plus or minus 0.2. We want to find what percent is that of 3.2. So we're going to do 0.2 over 3.2 times 100. So the radius is going to be 3.2 centimeters plus or minus. I'll just calculate that. Plus or minus 6.25%. Notice I'm not writing this to one significant figure. The rule for one sig fig is only for absolute uncertainties, so it's perfectly acceptable that, at least for now, I keep this as 6.25 because it's a percent uncertainty, not an absolute uncertainty. And so I want to find the uncertainty in the volume, and so I've known throughout the whole problem that what I need to do is find the percent uncertainty in the radius and add it to itself 3 times. Now, that's going to give me the percent uncertainty in the volume, and then after that I'm going to go back and convert percent uncertainty to absolute uncertainty, as you'll see. So the volume, the percent uncertainty in the volume is going to be the 6.25 added to itself 3 times. So the volume is going to be 137.26 cubic centimeters plus or minus 18.75%. And now I'm almost done. The question wants me to convert this into absolute uncertainty. And so my last, one of my last steps is going to be to find 18.75% of this number is equal to what? And so now I'm converting backward from percent uncertainty to absolute uncertainty. 137.26 plus or minus 18.75. I need to convert that to decimal times 137.26. And so the volume is going to be 18.75 divided by 100 times 137.26. That's going to be the absolute uncertainty. So 137.26 plus or minus 25.7 cubic centimeters. Now, if you go back and you look at the guidelines for uncertainty, you'll see there's a couple things wrong with this. Number one, this doesn't have one significant figure. Number two, even if it did, it doesn't have the same number of decimal places as our measured value. Here we have 2 decimal places, here we have 1, and so I'm going to have to fix this basically to get an acceptable final answer. So the first thing I'm going to do is, to be consistent with the IB guidelines, I'm going to round this up to 1 sig fig. 25.7 rounded up to one significant figure is going to be 30. And so this is going to be plus or minus 30 cubic centimeters. And now the last step is to make sure the number of decimal places is consistent. Because we had to round this to 1 sig fig, and in doing so, this now has 0 decimal places, we need to round our measured value to be consistent with that. And so 137.26, I'm going to round that up to 138, which has 0 decimal places, plus or minus 30 cubic centimeters, and that is the volume of the sphere. And now I'm done with the problem. And so it's kind of a lengthy problem, but again, as far as doing the problem goes, as long as you stick to the guidelines given to you in class for dealing with uncertainty calculations, you should be fine. This is a standard type of calculation problem that you should be expected to do. So make sure you understand in what situations do you add absolute uncertainties, in what situations do you add percent uncertainties. Remember the rules for having a consistent number of decimal places between the measured value and the absolute uncertainty, and make sure your absolute uncertainty only has one significant figure.